Hey, this is Scene Jordan, and I am presenting Lab 4 Oscillations for Physics 2211. The link for the lab's glow strip is in the description. So to start off, the goal of this experiment is to observe and record the oscillating movement of a mass attached to a spring and compare that to a computational model. The key concepts that will be used in this lab are the momentum principles, which are Newton's second law, to update the position and velocity of the mass, as well as the energy principles, which is the change in energy as it equates to the work done in the surroundings of a given system. Here are the equations that will be used to calculate all the values that will be needed. First, we have the velocity and position update formulas that uses the force acting upon the system to keep updating these values. Next are the energy equations, and starting out from the left, we have the kinetic energy, the gravitational potential energy, and the spring potential energy. It's worth noting that the S in the spring potential energy is a variable notation for the difference between the magnitude and relaxed length of the spring. The objective of this experiment is to create a computational model that creates an estimation for the energy and positions of the mass as it moves from the spring, and to see if this all respects the conservation of energy. Here we will make the system the Earth, spring, and mass to make the math a little easier, and to note that nothing is in our surrounding. It's worth noting that there is an assumption for this lab that does not account for heat. Here is the tracker model data that was gathered. The mass weighs about 0.402 kilograms. The spring constant is 6.82 newtons per meter, and the rest length or relaxed length is 0.123 meters. The initial position is about negative 0.08 in the negative x direction and about negative 0.6 in the negative y direction. Because we are at rest, the initial velocity will be 0. And the duration of the video that was captured was about 9.267 seconds, and the frame skips for the video is about 0.099 seconds per recorded frame. These are the initial conditions for the computational model, where we input the tracker data in all the given locations. There is also the section to type the formulas for the spring length and energies that we discussed in the previous slide. The formulas that are referenced per the code are being pointed at. These are the iteration conditions, which sets up the forces necessary to properly update the velocity and position over the given time frame. We further need to add the energy principles equations back into the iteration step to properly map out the changes in energy as time progresses in the model. And again, they're all pointing to the respective area in the code. Here you can see the results of the experiment with the graphs representing the changes in energy, the changes in the x position, and the changes in the y position. Possible errors can be found from human error from when setting the center of mass in the tracker model, lack of clarity in the video, which makes it harder to put the center of mass in the tracker model, and also not accounting for other forces acting on the mass. Now, was the energy principle satisfied? The answer to this is yes. If we look at the energy versus time graph, you can see that the orange line denoting the change in energy is always 0. This means that the energy was conserved and not lost, rather it changed form. The equation at the bottom of the slide shows this idea in a formulaic form. Furthermore, how did the positional estimates per oscillation compare? So in order to do this, we need to find the position at the beginning and end of a certain oscillation. The graph on the right shows an example of where you can find the difference between an oscillation loop. But the location that you choose does not really matter as long as the two locations you do choose are equally at the beginning and end of an oscillation. After doing this for both the x and y positions, we see that the difference is about 0.159 seconds. Now, what does this mean? Well, the lower this difference is, the more accurate the spring potential will be. This difference also accounts for other resistances that may or may not have been accounted for, such as air drag or video footage. That is the end of this presentation. Thank you for listening.